Hello, this is Tim Smith, the Academic Support Coordinator for St. John's River State College, St. Augustine campus. This video, an introduction to infinite series, is designed as a study aid and supplement to the math tutoring services offered at St. John's River State College. In this video, we will be discussing the partial sum, telescoping series, geometric series, and harmonic series. If a sub 1, a sub 2, a sub 3, and so on through a sub n is a collection of numbers, the expression, the sum from k equals 1 to infinity of a sub k equals a sub 1 plus a sub 2 plus a sub 3 and so on through a sub n and beyond is called an infinite series, or is sometimes referred to more simply as a series. The numbers a sub 1, a sub 2, a sub 3, and so on through a sub n are called the terms of the series, and the number a sub n is called the nth term, or the general term of the series. Given a sequence a sub 1, a sub 2, a sub 3, and so on, the sum of its terms would be the sum from k equals 1 to infinity of a sub k. To define a sum of an infinite series, we use a sequence s sub n, defined by s sub 1 being equal to a sub 1, s sub 2 being equal to a sub 1 plus a sub 2, which equals a sum from k equals 1 to 2 of a sub k. S sub 3 equals a sub 1 plus a sub 2 plus a sub 3, or the sum from k equals 1 to 3 of a sub k. S sub n then equals the sum of all terms up to a sub n, or the sum from k equals 1 to n of a sub k. The sequence S sub n is called the sequence of partial sums of the series from k equals 1 to infinity of a sub k. For example, find the fourth partial sum of the following series, the sum from k equals 1 to infinity of 3/4 to the k minus 1. The sum of the first four terms would be 3/4 to the 0, plus 3/4 to the first power, plus 3/4 squared, plus 3/4 cubed. We take the exponents to get 1 plus 3/4 plus 9 over 16 plus 27 over 64. We set each term to the least common denominator of 64, or 64 over 64 plus 48 over 64 plus 36 over 64 plus 27 over 64, which equals 175 over 64. If the sequence S sub n of partial sums of an infinite series, the sum from k equals 1 to infinity of a sub k, has a limit s, then the series converges and is said to have a sum of s. If the limit, as n approaches infinity, of s sub n equals s exists, then the sum from k equals 1 to infinity of a sub k also equals s. If the limit equals infinity or does not exist, then the infinite series diverges. A telescoping series is one where the middle terms in the series cancel. Let's consider the sum from k equals 1 to infinity of the quantity of 1 over k plus 2 minus 1 over k plus 3. S sub 1 would then be 1/3 minus 1/4. S sub 2 would then be 1/3 minus 1/4 plus 1/4 minus 1/5. Here, minus 1/4 plus 1/4 cancels, leaving 1/3 minus 1/5. S sub 3 then equals 1/3 minus 1/5 plus 1/5 minus 1/6. In this term, the 1/5 cancels, leaving 1/3 minus 1/6. This means S sub n equals 1 over 3 minus 1 over n plus 3. We can now take the limit as n approaches infinity of S sub n, or the limit as n approaches infinity of 1 over 3 minus 1 over n plus 3. The limit of 1/3 is 1/3, and the limit as n approaches infinity of 1 over n plus 3 is 0. 1/3 minus 0 equals 1/3. Therefore, the sequence converges to 1/3. A geometric series is one of the form the sum from k equals 0 to infinity of a times r to the k. This is equal to the sum from k equals 1 to infinity of a times r to the k minus 1, which equals a plus a times r plus a times r squared, and so on, including a times r to the n minus 1. This equation holds when a is not equal to 0, is called a geometric series with a ratio of r. If the absolute value of r is less than 1, then the series converges. If the absolute value of r is greater than or equal to 1, then the series diverges. When this series converges, the limit of the partial sum can be found by taking a over 1 minus r. For example, let's determine whether the following geometric series converges or diverges. The sum from k equals 1 to infinity of the square root of 2 to the k minus 1. This series will equal 1 plus the square root of 2 plus 2 plus 2 square root of 2 plus 4 plus 4 square root of 2 plus 8, and so on. This series is of the form the sum from k equals 1 to infinity of a times r to the k minus 1, where r is the square root of 2 and a equals 1. Since the square root of 2 is greater than or equal to 1, then the series diverges. In another example, we'll again determine whether the following geometric series converges or diverges. This time the sum from k equals 0 to infinity of 2 to the k plus 1 over 3 to the k. First, we need to put the sum into the form the sum from k equals 1 to infinity of a times r to the k minus 1. Since the sum starts with k equals 0, we'll take the 0 term, 2 to the 0 plus 1 over 3 to the 0. This equals 2. So we'll put that before the sum sign as an addition and change the sum to start at k equals 1. Next, we separate the numerator and gain a common exponent. 2 to the k plus 1 equals 2 times 2 to the k. Next, we take the 2 and move it out in front so that the common exponent k can be moved outside of the parentheses, 2 over 3 quantity to the k power. Since we need the exponent to be k minus 1, we take 2/3 outside, so it equals 2/3 times the quantity of 2/3 to the k minus 1 power. Multiply 2 times 2/3 to get 2, plus a sum of k equals 1 to infinity of 4/3 times the quantity of 2/3 to the k minus 1 power. Now the sum is in the form we need with a equal to 4/3 and r equal to 2/3. Since 2/3 is less than 1, the series converges. To determine the limit of the partial sum, we apply a over 1 minus r with our known terms. In this case, we also use the 2 in front of the sum sign, or 2 plus 4/3 over 1 minus 2/3, or 2 plus 4/3 over 1/3. This simplifies to 2 plus 4, or our final answer 6. The series converges to 6. The series, the sum from k equals 1 to infinity of 1 over k, is a harmonic series. This series can be expressed as 1 plus 1/2 plus 1/3 plus 1/4, and so on. If one considers the limit as n goes to infinity of 1 over n, which equals 0, one might expect this series to converge to 0, but this does not happen. It is more accurate to observe the partial sum. In this case, s sub 1 equals 1, s sub 2 equals 1 plus 1/2, s sub 3 equals 1 plus 1/2 plus 1/3, and we could go on. For this proof, we'll use s sub n and take it out 8 places. This gives us s sub n equals 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, and so on, including plus 1/n. Let's start with the first two terms. S sub 2 equals 1 plus 1/2. Then let's partition the third and fourth terms, 1/3 plus 1/4. If we substitute 1/3 for one of the 1/4ths, that will make the sum for which s sub 4 is greater than our 1/4 plus 1/4 equals 1/2. We can do this again with the next four terms, replacing the first term of those 4 with 1/8. The sum of these 4 terms is 1/2, and still s sub 8 is greater than this sum. If we do this to infinity, 1 plus an infinite 1/2 diverge. Since s sub n is greater than this sum, it must also diverge. As a final example, let's determine if the following series converges or diverges, and if it converges, calculate where. The sum from k equals 1 to infinity of 1 over 100 to the power of k. This appears to be similar in form to the harmonic series, but let's evaluate it to be certain. Since k is an exponent, if the series converges to a sum, then the series will take the form of a sum from k equals 1 to infinity of a times r to the k minus 1. First, remove the k to make the equation 1 over 100 to the k. Then we take a 1 over 100 out to make the exponent k minus 1. The series then matches the form where a is equal to 1 over 100 and r is equal to 1 over 100. The sum can now be shown to converge at a over 1 minus r. When we plug in our values, we get 1 over 100 over 1 minus 1 over 100. We simplify to get 1 over 100 over 99 over 100, which will simplify to a final answer of 1 over 99. Therefore, this series converges to 1 over 99. If you have further questions on this or any other math topic, or wish in-person tutoring, please consult the Academic Support Coordinator on your respective campus. Thank you, and good luck with your studies.